In this video, we're going to talk about exponents. So you want to remember that when you're dealing with an exponent, where here n is a positive integer, a to the n is just a times a times a bunch of times. So in fact, n times. Okay, so that's always what's happening when you have an exponent. So with this in mind, it's not easy. I mean, it works even when n is not a positive integer for these rules. But I'm going to sort of show them to you with m and n as positive integers. So using this idea, we can show that these rules work. So I'm going to write the rule, and then I'm going to try to explain it on the side here. So x to the m times x to the n. So notice that the base here is the same. So that's important. So I can rewrite this as x to the power m plus n. Okay, so if I think about what's going on, this is x times x times x, okay, m times. And then I have again x times x, n times. So in total, there's going to be m of them plus n of them. Okay, so that's why I have m plus n as the exponent. Okay, now this one you can write, so it's x to the m times n. You can write that as x to the m. I should have written it the other way actually, but you can write it as x to the m to the power n, or x to the n to the power m. Okay, it doesn't actually matter. So I'm just going to show one of them. So if I do x to the m n times, so that's going to be, oops, x to the m times x to the m, okay, n times. I'm just going to write n here. So each of those is actually x times x m times. Okay, so each of them, so the whole thing, this happens n times, but each of these is m times. Okay, but then the whole thing is n times. So then I'm going to have n times m x's in total, which is what this would mean. Okay, now when I have, again, the same base, x to the m over x to the n, you can write that as x to the m minus n, so you subtract the bottom. So again, this is just because you have x times x m times over, again, x times x n times. Okay, and they're going to cancel out. So some of them would cancel, okay, and depending on which one is bigger, okay, so when you're canceling, the most I can cancel is n of them. So if you have m on the top, you're going to get rid of n of the bottom, from the bottom, and you're left with m minus n. Okay, so if you have x times y all to the n, you can actually write that as x to the n times y to the n, because it's like xy times xy times xy, n times. And then if you rearrange, you can actually write it as x times x n times, and then y times y n times. Because they're all multiplying, it doesn't matter what order you write them in. Okay, so similarly, this one's going to work. I'm not going to explain this one with writing it, but it's going to be x to the n over y to the n. Okay, so when you have multiplication inside or division inside, the power can just jump in, okay, to both things. When it's addition on the inside, or subtraction for that matter, So this one I do want to explain. So this one would be x plus y times x plus y a bunch of times. So in fact, n times. Okay. So if I can't rearrange these to be x to the n plus y to the n, because if I was going to try, I'd have to FOIL this all out. Because when you have multiplication with addition and subtraction, you have to do all of them. So that doesn't work. So in fact, my rule here is actually a not rule. So this is actually not equal to x to the n plus y to the n. Okay, so that one does not work like you think it might. Okay, because you'd have to expand everything out and you'd get lots of other terms. Okay, so try to remember that one does not work. Maybe let's just highlight it to make sure that we notice that it's different. Negative exponents. So if you have x to the negative n, you can actually just write that as 1 over x to the positive n. Okay, so to take that further, let's try and simplify this expression, which is not easy. So what I would do is make them all fractions. So x to the minus 2 minus y to the minus 2 over x to the minus 1 minus y to the minus 1. So that's going to be 1 over x squared minus 1 over y squared divided by 1 over x minus 1 over y to the power 1. When it's power 1, we don't have to write it. And now we're back into something we did in the previous video, the factoring video, or the fractions video. So now I have a complex fraction, so a fraction within a fraction. So remember we had two methods to simplify. So one of them is to make common denominators, so to simplify the top and the bottom separately. The other one is to multiply by the common denominators. Either way, whatever you want to do. I'm just going to make common denominators, so I'll do the first method. So on the top, the common denominator is going to be x squared y squared. So that means I need to multiply this term by y squared over y squared. And that term by x squared over x squared. And on the bottom, it's going to just be x times y. So I multiply this term by y over y and this term by x over x. So that's going to give me y squared over x squared y squared minus x squared over x squared y squared. And that's all over y over xy minus x over xy. And now I can make these into one fraction. So the bottom here is x squared y squared, and it's y squared minus x squared. And down here I'm going to have y minus x over xy. And now I have division of fractions. So notice I have this fraction over this fraction. So I want to flip the bottom one and multiply instead. So it's going to be xy over y minus x. Okay, so that's going to be xy times y squared minus x squared over x squared y minus x. Okay, so then the x on the top can cancel with one of these x's on the bottom. The y on the top can cancel with one of the y's on the bottom. Again, that's because those things are multiplying everything on the top and everything on the bottom. Okay, so then this simplifies to y squared minus x squared over xy y minus x. Okay, now in fact I can simplify this more, but we haven't actually talked about factoring yet. But it's review, so you should know how to factor this top guy. So it's a difference of squares. So I have a square minus a square. Okay, so anytime I have that, we're going to see this in a later video, but a squared minus b squared, you can always factor as a plus b times a minus b. So we can factor this as y plus x times y minus x. And now we can see that the y minus x can cancel out. And I'm going to have y plus x over xy. Okay, so that would be a reduced final answer. Again, that's using the first method that we did before. You could do the other way where you multiply by the common denominator on the top and the bottom, and that would work and probably faster. But like I said, I usually prefer this method. Okay, now what about when the exponents are not integers? So exponents of the form 1 over n, they're special. So x to the 1 over n is called the principal nth root of x. And the way that we write it, so x to the 1 over n, you write it as the nth root of x. Okay, now we want to be careful. If n is even, then x has to be bigger than or equal to 0. Okay, but if n is odd, then x can be anything. Maybe I'll say x has no restrictions. Okay, so if n is, say, 2, 2 is the one we're most familiar with. That would be the square root. We know that we can't take the square root of a negative number. Okay, so that works for all even roots. So for example, 9 to the 1/2, this is the second root of 9, which when we have a 2, we don't write it. So it's actually just the square root of 9, okay, which we know is 3. Okay, now the principal nth root, it's for these, when n is even, it's always going to be a positive. So you might think, well, I should have plus or minus 3. That's not true. So the square root of a number is always going to be even. So don't get confused. If you had x squared minus 9 equals 0 and you wanted to solve, then you would have x squared equals 9. Then you would take the square root of both sides. So then you would get, then you have to add in the plus or minus. So here's where you get plus or minus 3. But what this is saying is just what's the square root of 9, and the square root of 9 is 3. Okay, so notice the plus or minus here is from taking the square root of both sides. So it's because it's this thing squared equals 9. So it's a bit different. Okay, so this I'm just notice this is different. Okay, so but a lot of people do get confused there. So now the rules that we had before still apply even when the exponent is rational or fraction. So if you take the nth root and then you raise it to the power n, that's just x. Okay, now again I should just write this is assuming the nth root of x is defined. Okay, so if it's n is even, then x has to be positive, no matter, even though the raising it to that power would get rid of the negative, you have to be positive there. And similarly, you can do the power first, but actually this one is a little bit more complicated. So it's just x if n is odd. Okay, but it's actually absolute value x if n is even. Okay, so this is a little bit harder to see, obviously, because it has two things going on. Okay, so if n odd, if x is bigger than 0, that means x to the n is going to be positive as well. And if x is less than 0, then x to the n, I'm raising it to an odd power, so it's still less than 0. Okay, now this doesn't matter, so then I want to take the nth root. Okay, so in both cases, I want the nth root of x to the n. So the n is odd here, so there's no restrictions on the inside. So it doesn't matter if this thing's negative or not, it just spits out the correct answer, okay, which is x. Okay, but the problem comes in when n is even, because if x is bigger than 0, x to the n is still bigger than 0, and the nth root of x to the n is going to be just x, because I'm going to get the positive answer, and x is positive. So x is the positive answer. But when it's less than 0, then x to the n is bigger than 0 because n is even here. So if I have a negative number and I raise it to an even power, I'm going to get a positive number. Okay, so then when I take the nth root of that, I can because it's positive, so my nth root is defined, but I'm going to get a positive number which is not x. Okay, it's absolute value x. So it's going to be like x, but it's going to be the positive version. So that's why we have to use the absolute value. Okay, that was a long explanation for something that doesn't come up very often. But so root n of x times root n of y. This is the nth root of xy. Okay, this is the same as rule 4 I wrote earlier. So it's just x to the 1 over n times y to the 1 over n. So when they have the same power, the rule's written this way. So if I had xy to the 1 over n, you could rewrite it like that. Okay, that's what this one is doing as well. So similarly, the nth root of x over the nth root of y is, you could write it as the nth root of x over y. And that one was, rule 5, I think. The same before. Just a note. I don't think I have it here. No. So like before, if I have the nth root of x plus y or minus y, you cannot split it up. Okay, so that does not work. So only for multiplication and division does it work, not for addition or subtraction. So you can also, so far everything we've had has been 1 over something, but you could have m over something. And if it, so m over n, which you could write as m times 1 over n. So because of that, x to the m over n, we could write as x to the m times 1 over n. And when you have multiplication of exponents, remember you can write that as x to the m to the 1 over n. Actually, let me just rewrite that. So you could write it x to the m to the 1 over n, which would be the nth root of x to the m. Or you could write it as x to the 1 over n to the power m, which would be the nth root of x all to the power m. Okay, so both of those are the same. So if we wanted to simplify, so this is where it gets tricky. So you need to know your exponent rules for something like negative 27 to the 2/3. This exists. And we can actually simplify this and find an exact answer. But if you entered it in your calculator like this, your calculator is not smart enough to know. So it's going to say error. So it won't actually tell you the answer. So if we wanted to simplify this, okay, so you could do it negative 27 squared and then take the cube root. I know that 27 is a cube, so I'm going to do the cube root first. So it's going to be the cube root of negative 27, and then I'm going to square it. So 27 is 3 times 3 times 3. So the cube root of that is going to be negative 3. And then when I square that, I'm going to get 9. Okay, now you could do it the other way where you square it first and then take the cube root. But then your numbers are going to be bigger because you have to square negative 27. So if I can, I usually do the roots first so that the numbers remain smaller. Okay, now you can also use these rules to simplify expressions involving radicals. So let's say I have square root of 1,000. Well, I know that 1,000 is 100 times 10. So the reason I wanted to write it like this is 100 is a perfect square. And now that I have it as multiplying, we know we can break it up. So this is the square root of 100 times the square root of 10. And I know the square root of 100 is 10. So it's 10 root 10. Okay, so that's a more simpler form. And then there's no perfect squares that divide 10. So that would be as simple as I could get it. Okay, similarly, root 2 and root 18 are both not nice. Although root 18 I could break down into be something nice because it's 2 times 9. And 9 is a nice perfect square. But I could also put these together as 2 times 18 under the square root, which is the square root of 36, which actually is a nice square. So then it's just 6. Okay, now this one is a bit trickier. So I can actually simplify this even though the roots are different. So I have root of 18 of 2 root of 18 minus 5 root of 8. So what I'm going to do is I'm going to break both of them down. So like I said before, 18 I could write as 2 times 9. And 8 I could write as 4 times 2. So again, both of these are nice perfect squares. So they're going to become integers. Okay, so that's 2 times root of 9 times root of 2 minus 5 times root of 4 times root of 2. And then we know that root of 9 is just 3 and root of 4 is just 2. So let's just emphasize that. So this thing is equal to that and this thing is equal to that. So I just replace those. And now I have 2 times 3 is 6. So I have 6 root 2 minus 5 times 2 is 10. So that's 10 root 2. And now I have a like term. So these both have root 2's in them. So there's 6 of them here, minus 10 of them here. So maybe right away you know that there's minus 4 of them. Or you can sort of factor out the root 2, and then you'd have 6 minus 10 left over, which is again minus 4. So this is minus 4 root 2. And that would be our final answer. So that is working with some radicals. So again, all of these things I did for square roots because those are the ones we encounter the most. But it didn't matter that these are square roots. So if it was a cube root, for instance, then I would want to simplify, try and pull out perfect cubes instead of perfect squares. Okay, so here I pulled out 100. Well, if this is a cube root, 1,000 is actually just, the cube root of 1,000 is 10. So that would be even nicer. But then you want to look for perfect cubes instead of perfect squares. But all the rules work the same way.